Atlega. Regular model screen is not clear. Atlega.
Amul, songs are not displaying. Prayer song is not displaying.
Sometimes అనిపిస్తుంది.
Mic off.
on off your computer.
The sun comes up.
Hello. Song is stopped. Hello.
Thank you all. Now I invite our beloved principal, Dr. Sister Shaini KP, to deliver the welcome address.
Good evening to everyone. A warm welcome to the international webinar on innovative approaches in green chemistry for addressing emerging challenges in chemical and allied sciences. Taking place from September 10th to 14th, 2024. We are thrilled to have participants from across the country join us for this exciting and enriching event. I would like to extend my sincere appreciation to our esteemed speakers and resource persons for generously accepting to share their expertise. Your insights will be invaluable as we explore cutting-edge advancement in green chemistry and their role in taking contemporary challenges. Green chemistry represents a transformative approach that emphasizes environmental sustainability and safety. This webinar will delve into innovative solutions and eco-friendly practices that enhance efficiency and promote a greener planet. A special thanks to Dr. K. Nirmala Jyoti, the convener and the head of the Department of Chemistry, for organizing this event, and to Dr. V. Sumalata, Mrs. M. Shakina Kumari, and Ms. G. Esther Rani for their efforts in leading this webinar. I hope this webinar brings fresh perspectives, new knowledge, and renewed enthusiasm. Wishing all a fruitful and enriching experience. Thank you.
Thank you, sister, for your valuable and informative message. Now let me brief the significance of the webinar. Good evening, distinguished speakers, participants and colleagues. Welcome to 5-day international webinar-cum-Faculty Development Program on Innovative Approaches in Green Chemistry for Addressing Emerging Challenges in Chemical and Allied Sciences. We are delighted to have experts, scholars, and participants from around the world joining us for this enriching webinar. It's my privilege to address you all today as the convener of this webinar and highlight a few focal points on the topic. Innovative approaches in green chemistry are essential for addressing the emerging challenges in chemical and allied sciences. The significance of these approaches lies in their ability to create more sustainable, eco-friendly processes and materials that minimize environmental impact while enhancing efficiency. Green chemistry focuses on reducing the use of hazardous substances, conserving energy, and developing renewable feedstocks. By embracing innovative techniques such as catalysis, green solvents, and energy efficient processes, industries can significantly reduce waste, lower carbon footprints, and promote circular economy principles. These advancements also align with global sustainability goals, tackling issues like pollution, resource depletion, and climate change while fostering economic growth through environmentally responsible technologies. This interdisciplinary approach has the potential to revolutionize industries such as pharmaceuticals, agriculture, and energy, pushing boundaries towards safer and more sustainable practices. Hope much light will be thrown on these areas during the sessions ahead by the experts in the field with fruitful interaction of you all. Now I request Dr. G. Jyoti Valivia, Assistant Professor, Department of English, to present the biodata of today's keynote speaker, Dr. Srinivasa Rao Amarneni, Professor in Department of Chemistry, Bangalore.
Olivia, voice is not audible. Please. Voice is not clear.
A very good afternoon to all the guests, special invitees, fraternity, academicians, and aspirants. A warm welcome to you all for this 5-day international webinar from FDP on innovative approaches in green chemistry and addressing emerging challenges in chemical and allied sciences. I am extremely delighted and honored to introduce our today's keynote speaker, Dr. Srinivasa Rao Amarneni. He was born at Pedamaddur village of Guntur district, completed his graduation in Guntur, and obtained his master's degree as well as PhD from Andhra University, Visakhapatnam. He started his career as a senior chemist in Orca Pharmaceutical Laboratories Private Limited, Hyderabad. Later, he worked as assistant professor, associate professor, and professor at several reputed institutions like Dept University, Visakhapatnam, MITS Raigada, Orissa, PUS Institute of Technology, Dayananda Sadar Academy of Technology and Management, and Dayananda Sadar Institutions, Alliance University, and Dayananda Sadar University, Bangalore. At present, he is working as a professor in chemistry at East Point College of Engineering and Technology, Bangalore. His research area of interest is interdisciplinary research in the fields of analytical and environmental chemistry, nanotechnology, water technology, and phytochemistry. He had considerable experience in the research field of 3D dotting of protein with ligands. He has 25 years of teaching, 25 years of research experience, and approximately 1 year in industrial experience. As an acute observer and a passionate academician, he has attended 21 national and international conferences and published 25 research papers, authored 1 book, contributed 2 chapters, and communicated 3. To his credit, one of his papers is published in the top 25 hottest articles in ScienceDirect.com journal. Around 14 posters presented in international and national conferences. In addition, he attended about 13 Nobel laureate lectures and conferences and workshops. He worked on research contribution on cloning, expression, purification, and crystallization of Mycobacterium tuberculosis, expression, purification, and crystallization of cytochrome P450 enzyme at Edinburgh University, Edinburgh, Scotland. He is an international national fellowship awardee for research and teaching at DAD, Germany, Royal Society Scotland RSC, DWF England, Germany, UFZ Center Germany Fellowship, Erasmus Mund each visiting scholarship or fellowship, teaching and research fellowship of Finland University, etc. He held many academic responsibilities and professional recognition as a Fellow of Royal Society of Chemistry, London, Chartered Chemist and a Chartered Scientist, awarded by RSC, and a member of American Chemical Society, USA, member of UK Biochemical Society, UK, in DGMS, Germany, a member in International Society of Bioinorganic Chemistry, in Indian Association of Crystallography, in Society of Biological Inorganic Chemistry, India. He was invited and delivered a talk in FDP program on environmental biotechnology organized by VTU and PCIT, and chaired the session in ISTAM International Conference at Alliance University. He was adjudicated PhD thesis from 4 universities and directed 6 PhD students from Dayananda Sadar University. He is a polyglot and an eloquent speaker. Now we are very glad to have such a multifaceted personality amidst us. Now he is going to deliver a talk on green analytical chemistry, approaches on environmental analysis and sustainable development. I welcome you, sir, to continue the session. Over to Dr. Srinivas Rao, sir. Thank you.
Thank you so much, and good afternoon to all of you. Firstly, I would like to thank to the organizer and also the Dr. Venkatana for the opportunity given to me to interact with you, all of you. First, I would like to share.
Sir, please raise your voice little. We are not able to hear properly.
Yeah. So now, good afternoon, all of you. Am I audible now?
Yes, sir. Audible.
Yes.
Yeah. Thank you. Sometimes the technical issues are here.
Yes, sir.
Internet of all this. So, can you inconvenient excuse me for any inconvenience technical issues? So, good afternoon to all of you. And I'd like to thank all of, to the organizer for the opportunity given to me to interact with all of you. So, today my talk is on green analytical chemistry approaches on environmental analysis and sustainable development. And the outline of my presentation is the green chemistry and green analytical chemistry, overview of the green chemistry, green analytical chemistry, and also the United Nations Sustainable Goals. And also we will discuss about the multi-component chemical reactions, that importance in the green chemistry, and also we'll discuss a few examples relating to the multi-component chemical reaction. And also we will discuss in brief about the biopolymer in green chemistry and case study in the food packaging, agriculture, health sector, and also energy sector. And nanotechnology applications in the green chemistry, and also particularly nanofertilizers, how it is important relating to the green chemistry, nanopesticides for agriculture purpose to reduce the climate in the impact of the climate change. Hydrogels and biopesticides are important in agriculture. That is a green chemistry practices. So we will discuss also biohydrogen production by electrochemical methods. Now, also we'll discuss about the artificial photosynthesis for the CO2 reduction and green methods for few green methods for the water purification. And lastly, we'll discuss a little bit like a more detail about the green chromatography, green laboratory practice. And finally, we will conclude the presentations. And I'll start with the overview of the green chemistry. Green chemistry is mainly design of the product and also the process to reduce the and eliminate the use of the toxic substance, minimizing the waste, and also promoting the environmental friendly practice, and also which support the sustainable development. And let us look at the difference between the traditional chemistry practice and also the green chemistry practice, and how the green chemistry is important, and also many of the scientists are attracting to the green chemistry research area. And if you would consider the traditional chemistry, the high accumulation of the waste generating high risk of accidents, and also it produces the non-degradable products, and also the derivatives also will be using in the traditional chemistry practice. And also it releases to the additional byproducts, and which are considered as a highly toxic. And in the case of the green chemistry, it prevents the accumulation of the waste. That means when you when you adopt the green chemistry practices for the research, and it reduces the less or minimizing the toxic waste, and also utilization by using the utilization of the biocatalyst, and also renewable use of the renewable precursor, utilization of the safer solvent or the green solvent and the reagent, design of the potentially benign nanoparticles, means environmentally friendly nanomaterials, and high atomic economy and less hazardous synthesis, means the less amount of the reactants, and it produce the good products, and high yield can be observed by following the green chemistry. Now let us look at the green chemistry goals. Green chemistry goals are the prevent of the pollution, minimize of the hazardous material, maximize the efficiency, and avoid the release of the toxic solvent, and also efficient utilization of the raw material, and also it eliminates the waste which affect the environment. And green chemistry to meet the to meet the green chemistry practices that includes or correlate by following the green catalysis, efficient process, and environmentally benign products, and also green and renewable raw material, and the green solvent. By using the green solvent, and also the different catalysts like a biocatalyst and biopesticides and enzymes in the reaction that give you the single product without forming the product without formation of the waste products. So only the reactants, and we will get the directly product without forming the waste. So that is one of the practice approach for the green chemistry. So we'll have a later stage, we'll see some of the examples relating to the multi-component reactions, the practice in green chemistry. And also Green chemistry is a interdisciplinary aspect, and it involves the biology, toxicology, and ethics and philosophy, economics, and engineering research, engineering technology, and environmental science. So this green chemistry is the interdisciplinary work. And the benefits of the green chemistry is that fewer synthetic steps and often allowing a faster manufacturing of products and increasing the plant capacity and saving the energy and the water. So fewer synthetic steps means, as I mentioned, that when you want to design the or synthesize the product, so it should not be more in a, as earlier we mentioned, we discussed that the conventional traditional method, traditional chemistry practice. So if you want to have the formation of the product, we need to use the reactants are also more, and also many number of steps are included before the product formation. So, and also waste also can be generated. So by following the green chemistry, the benefit of the green chemistry, you can get the products and the reaction and the reactants and the product in a form, product will be takes place in a single step in presence of the catalyst, biocatalyst, and enzymes, all and in presence of the catalyst, and also in presence of the green solvent like water and liquids and all that. So often allowing faster manufacture, and when you apply the green chemistry process, yeah, the reaction, manufacturing process also will be faster, and increasing the plant capacity and saving the energy and the water also. By following this green chemistry practice, you can reduce the energy consumption and also the water. And the reduced waste, another benefit of the green chemistry is that reduce the waste and eliminating costly remediation and hazardous waste disposable and the removal of the technology to treat the pollutant. So when the costly cost effective cost involved in the treatment of the process, when you are manufacturing some product by a company, it produces a lot of the waste, and again it has to be treated before releasing to the environment. So to treat those chemicals, those liquid effluents or gaseous effluent, it involves a cost. So if you follow the green chemistry method, so first of all, waste will not be generated, first of all, and it will be completely avoid or minimize it. So removal technology to treat the pollutant, and green chemistry also is important in treatment of the environmental pollutants. By following, as I told you, to biodegradation, bacteria can be used, and some enzymes also can be used for the degradation of the chemical or toxicants to non-toxicant. Like for example, pesticides, polycyclic aromatic hydrocarbon. So that can be degraded into the non-toxic chemicals by following the green methods, like using the green catalyst, green solvent, and electrochemical process. That all is relating to the green chemistry. And one more point here we'll look into that the structure of the chemical enterprises towards the sustainability. So any company, when they are manufacturing, they should they should keep in mind about the sustainable, environmental sustainable. Whatever the product the releasing by that company, that should not be affect the environment, and either it is a human or the organism, or biological system. So for that, they have to follow the certain thing, and they should use the environmental sustainable matrices, and water consumption also be less, and energy consumption like solar and other energy should take for the application of the industry, like hydrogen generation from the electrolysis, that type of, or solar energy, that type of the renewable energy can be used for their industrial application. So that is those practices are important for the to meet the environmental sustainable practice. So here the green chemistry involves the 12 principles, which minimize or eliminates the use of production of unsafe substance. That the 12 principles include is prevent the waste, minimize the atom economy, means that the stoichiometric reactions, so how equal amount or less amount of the reactants to form to produce the product, and less hazardous chemicals, and also safer chemicals should be used, and safer solvent and the reaction conditions also should be taken into the consideration, and increase the energy efficiency, use of renewable feedstock, and avoid the chemical derivative, uh, and also use of the catalyst. Here the biocatalyst also can be applied, included in the formation in the production of the any product. Design of the chemicals and the products to the degrade after the use, and there is some certain green chemistry practice to degrade the or transform the parent compound to which is considered as a toxic compound, toxic nature, into non-toxic. As I mentioned earlier, bacterial means like biocatalyst, which are not affect the environment. Some of you may get the doubt: is catalyst also is affect to the environment? Catalyst, the reusable catalyst can be used. Some of you may ask the question. So catalyst also is one of catalyst also some metals, na? So nanomaterial, metal oxides, those also can be affect the environment. So there are some practices, some groups are working on that, reusable or natural catalyst like geolites they are using to degrade the toxic chemicals into non-toxic chemicals, and analyze the real-time prevention of the pollution. Here you might have, some of you might have known that there is a real sensors all there, sensor, biosensors, solid state electrochemical sensor. So you can monitor like a DIVO, dissolved oxygen, chloride sensor, chemical oxygen demand sensor. Even you can make the automation of the STP, standard sewage treatment plant, and also the sensors application in the water, drinking water purification systems also. Later, some example we'll discuss more detail. Minimum potential for the accidents and also the safe aspects. So these are the 12 principles which are involved in the green chemistry, and this was introduced by the Paul and ENTAS from the EPA, Environmental Protection Agency of USA, and also along with the John Warner. They have introduced the green chemistry practices. So these are all the 12 principles of the green chemistry. And now, green analytical chemistry, overview of the green analytical chemistry. So sustainable practice in a green analytical chemistry lab are essential in light of the global environmental concern and to support the United Nations Sustainable Plan. So sustainable practice, this is also one of the good promising research area. When you are a good manufacturing practice, GMP, all those are comes into the sustainable practice in a green analytical chemistry lab. So you have to be keep in mind about the environmental safety, and also that whatever the practice that you are adopting in the chemistry lab, and that should be aligned with the United Nations Sustainability Plan. So, for example, when you are extracting the chemical compounds from the matrix, natural products, for example, you can't use the toxic solvent. You should use the green solvent. And also, consumption of the solvent should be less, and you can extract the more compound from the that matrix, plants or soil or whatever. So that all, and also discarding the chemicals, that all is involved into the sustainable practice. So sample preparation onwards to end of the analysis, you have to take care of those or you have to follow the green analytical chemistry practices. So whatever the waste that should generated from the laboratory, analytical chemistry laboratory should not affect the environment. And also reducing energy use. Let us take some example. In coming slides, I can give some example relating to that. Reducing energy use, choosing consumables that minimize the waste, and also optimizing the lab process and support the sustainability. So when you are selecting the reactants and or method development, what are the solvent that is required? So if it is a toxic solvent, you have to be find alternative solvent, as I mentioned earlier, like a green solvent. That is an example. And reducing the energy usage also in laboratory practices. So green analytical chemistry includes the green sample pre-treatment. So there are some protocol, and where you need not use much solvent for your sample pre-concentration. That is one aspect. And green solvent, again I am repeating, miniaturization of the analytical device. Here the so there are some sensors also can be used instead of the sample treatment, directly real-time monitoring of the any analyte present in the environment using a portable sensors or analytical devices. So reduction in the waste of generated, ensuring the use of the proper waste treatment methodology, that all are considered as the good practice in a green analytical chemistry lab. Greenness of the analytical technique include the green chromatography, high performance liquid chromatography, where the green solvent being used for the analysis. Green solvent selection based on the solvent selection means which is solvent which you are using for this analysis, that should not affect the environment. And also design of the experiment is important, is a statistical tool for the quality by design. Quality by design. There are some softwares are there. Some of you might have aware of that. Nowadays, there are some of the softwares there. Molecular docking. Some of you might have heard about the molecular Schrodinger, Gold, and all those things. So these are these softwares are using for the drug designing. So before going for the wet lab experiment, they're using these software. So how the molecular biomarker that interacting with the molecule, designed molecule. So they can predict before synthesize. So whether it is a strong interaction or the weak interaction, that all these. So there are some similar to that. There is some design of experiment, some free softwares also there. So when you are varying the parameter, temperature, pressure, and all that, what would be the product formation, that all will be known by using that that software. So here the green analytical chemistry in combination of the design of experiments of softwares, and you can produce, you can generate the robust analysis and also the good product. And that analysis by mass spectrometry, HPLC, and vibration spectroscopy, and also gas chromatography. These are all the important practices in a green analytical lab. And also green analytical chemistry lab involves the sample preparation without using much sample for to extract the analyte, and use suitable solvent, suitable reagent, and suitable instrument should be used, where you can't use a huge energy consumption, that all should be avoid. And operating safety also is important, and waste should not be generated. Method also is important. The automated analysis using that method, green solvent, and also in situ and online analysis. As I told you, using the in situ method means you use the design of experiment protocol. Online analysis means you can use the sensor, so real-time monitoring can be involved, like a sensor. COD or dissolved oxygen sensors at all. Next one, green analytical chemistry, sustainable chemistry, and engineering research to support the United Nations Sustainable Development Goals. As I mentioned earlier, in 2015, in every university, every industry in India and also the abroad, these universities also has to follow the United Nations Sustainable Development Practices plans, and that includes the sustainable development goals. Aim is providing the guidelines applicable universally to all the nations for equitable and responsible development and respectable of the humans and ecosystems, avoid the impact of the pollution. So these are the different, 17 United Nations Sustainable Development Goals, and in that 13th, climate action and also the affordable clean energy is relating to the chemistry, green chemistry principles. So green analytical chemistry practices are involved, as I told you, sample preparation and the analysis and all these are involved in the green analytical chemistry laboratory practice principles. Now, one of the, I request, dear colleagues, I request you to mute your mic. Yeah. So let me continue to discuss about the green chemistry sustainable practice by the multi-component reaction. Multi-component reaction. And multi-component reaction in organic synthesis pursuit is the one of the green chemistry practice. What is the multi-component reactions is that in a single part, two or more reactants can be used and form the single product and with a single step. Those are called multi-component reactions. So this is multi-component reaction in a green chemistry is a important practice. So that means no wastage, no the toxic solvent being used in the multi-component chemical reaction. So green synthesis using the catalyst, green catalyst, the design of the degradation, real-time waste, real-time monitoring or analysis, waste prevention, all these relating to the green synthesis. So that means only the product only will be formed with a high yield without forming the any waste product. And also another important aspect is that multi-component reactions, example like a sticker reaction, Ewald reactions, all these reactions are involved or example for the multi-component reaction. So one example case study for the multi-component reaction in the green chemistry is a ethanol water as a green solvent medium. An efficiency of the green synthesis of highly functionalized N-methyl-2-nitroaryl 1H-benzochromen 3-amine derivative under the catalyst-free condition. So if you look at this example, and equimolar amount of these all three products, and it forms the single product without using the catalyst. So here the solvent will be a green solvent we are using. It is reported by this referent, and in ethanol and water, the solvent will be a ethanol and water as a green solvent. So the key feature of this reaction multi-component protocol are operational simplicity, mild reaction condition, and also the high yield also can be observed. This is one example for the green chemistry, that is the multi-component reaction. So one more example is, let us look at this. And green catalysis for chemical transformation, the need for the sustainable development. The catalyst development of a new catalyst is a challenging for the different chemical reaction that enable the reaction to occur under milder condition, reducing the energy consumption. Here, one example, you can look at these two reactions. One is the traditional reaction or chemistry practice, and also another one is the catalytic. Catalyst used in this reaction. In the first reaction, there is no catalyst, and it produces this is the reactant and this is the product, and this is the reagent they are using, sodium borohydride, and it produces the byproducts also. It is considered as a waste. But if you look at the second reaction, in presence of hydrogen, palladium and carbon combination, product formed without the waste generating. So this is one example for the hydrogenation of the ketone. So this is one example for the green synthesis and catalysis by using the catalyst. And also another example is that the basic ionic liquid. So the ion, as mentioned earlier, ionic liquid is one of the green solvent. So here these are the products that they are using. Earlier I told you MCR is nothing but the in one single part, two or more reactants can be used, and it produce the single product without forming the any waste products in presence of the solvent. In this case, at 80-degree temperature, and also green solvent, the ionic liquid is the 2-hydroxy ethyl ammonium formate as a is acting as a catalyst. So this is one example I consider as a case study for the multi MC or multi component reaction in a green chemistry. And another one example is that multi-component reactions in a water medium catalyzed by the zinc vanadium cobalt 3 hydrothalassite, a greener and efficient approach for the synthesis of multi-functionalized benzenes. So same in this case also. So 2 or more the reactants can be taken into the reaction part reactor, and in presence of water, and also it produces the single product and high yield and without forming the any waste products. One more example is consider in case of the multi-component reaction to enhance the more yield, photoredox multi-component reaction. Photoredox means in a single part you take the 2 or more component reactants, and in presence of the photolight, it may be UV or visible, and it forms the product without forming the any waste. So example, the beta functionalized diketones, synthesis of an N heterocycle components, alkene and alkane functionalization, drug precursor synthesis, like a API compound also, active pharmaceutical index, all these also can be designed using the combination of the photoredox mediated multi-component reaction. Previously, we have seen the multi-component reaction or reactions in green chemistry practice in presence of catalyst, without catalyst, and also in presence of the green solvent and without the green solvent also. And here this is one example for the catalyst-free multi-component reaction. Yeah. And ultrasound assisted multi-component reaction. This is also last example relating to the MCR in a green chemistry, multi-component reaction in green chemistry. In combination of the ultrasound assisted multi-component reactions in green chemistry, it synthesize of the N substituted 1,8-dioxy hydroacridinase using the beta cyclodextrin as a supermolecular reusable catalyst. So this is also reusable catalyst practice is important in a environmental aspect, and also in industry also. Otherwise, it will be causing as another impact on the environment. If you don't retrieve and recollect the catalyst, again it causing for the effect on the environment also. And this is one example. So ultrasonic assisted multi-component reaction. This is one example, and also one more example is that the deep eutectic solvent. This is also one example I am talking about the green practice of the green chemistry practices by following the multi-component reaction. Here, the solvent, deep eutectic solvent will be the combination of the organic solvent and inorganic solvent. So in the deep eutectic solvent presence, the compounds will be synthesized in a single step. That is one example. And here one more combination of the the combination of the electro-organic synthesis. Some of you can practice, some of you in your college, you can practice this type of experiments. It is not expensive also. You have to find out the suitable electrode. And electrochemical synthesis and reactivity of three-membered string carbo and heterocycles. And in this one, this is the electrochemical cell. Most of you know that it consists of the anode and also the cathode. Anode and cathode. At anode oxidation is taking place, at the cathode reduction is taking place. So near the electrode, this is the component, and these components near to the anode electrode, it will be oxidized. And in this case, the ring opening process takes place in this experiment. So what I wanted to say or mention here is that electro-organic synthesis is also one of the important practice in a green chemistry, and also easy also when compared with the. Then you can take one example. You can same study you can use the catalyst in presence of catalyst, and also in absence of catalyst, and in a combination of electro chemical process synthesis. So you can compare the all these method. That itself is one of the good research paper. You can plan in that way, comparing the method. So which method you can observe the good quality and good yield, that all you can report in your publication and all that. So this is itself one of the good what to start working in your college. And also one our example, multi-compound reactions for the synthesis of active pharmaceutical ingredients. So as I mentioned that API, active pharmaceutical index also, ingredients also can be synthesized with a single step by taking the 3 or 4 components or reactants. And so this is one example. That is a Strecker reaction, alanine. I'm not going to detail more. I already shared this PPT for your reference already. And also this is one of the examples for the drug synthesis, and in presence of the catalyst. And this is the phenytoin, and also the sorbitol, sorbinin is the product. By taking these are the reactants, and in presence of these reagents, and we can get the sorbinol, racemic, and also the phenylethyl. So these are the example for the API synthesis using multi-component reaction. So now another aspect of the green practice is the biopolymers. Most of you are aware of that. Biopolymers in a green and sustainable chemistry and the catalysis. Biopolymers in a food packaging made from the renewable sources like a plant and also the chitosan, natural polysaccharide, cationic polysaccharide, polypeptides, and also polyphenols. All these are source from the natural renewable biomaterials, and these materials are using in practice for the food packaging, and also like the biodegradable plastic nowadays. Most of the industries are switch over to the synthetic polymer, to the biopolymers. So why that happens, as you know that I'm not going to take much time to explain this one. You're all aware of all these things. Plastic is more impact on the environment, and particularly microplastic. When the plastic is entering into the soil and it converted into the, or because of the temperature and all the condition, and it produce the microplastic. And microplastic is a dangerous. Now you can work on this area. Some of you can plan some of the project. You can submit the projects to DST and all the funding agency. Microplastic detection is also important. But there is a challenging aspect here is that you have to how to isolate the microplastic in a water. Even you can find the microplastic in the water bottle, and also some of the food storage in the low quality plastic material, plastic container. So microplastic is entering to the environment. Finally, it reaches to the human system, and that is also there are some reports. Some of the Norway professor group who have forgotten his name, and those group reported that India also some maybe in Mandi IIT they reported the microplastic in a blood sample. So here the challenging point is that how to isolate the microplastic. Along with that, many other junk material will be there. You have to be isolated. Like you have to use GCMS pyrolysis, GCMS method, or the FTIR, that all those things. But why I'm explaining all these things? You can get some good idea more than this for your project or funding purpose. I'm explaining this one, mentioning here. And application of the biopolymers is in a wound healing, biomedical application, drug delivery. Why does all happen? Considering for the drug delivery and wound healing is that it is easily degradable. That is one name. And also these biopolymers can't be effect on the or interact with the other molecules in the biological system. So that is another advantage of the biopolymers that are using in the different fields. medical and also the drug carrier. Even there are some groups are working that drug carrier by the nano materials. So there are again the group has worked that drug carrier nanomaterial used for the drug carrier that gives a toxic effect. That also be there to avoid all these those things. Biopolymer is the best polymer, but best material that will not affect the any organisms in the human body, even if you use the drug delivery purpose. And tissue engineering also, when tissue growth, that all purpose also will be using biopolymers are being used. And also biopolymers are using in the biosensors. So this is one area. Again, I'm referring this this point here in this juncture. The biosensors also one of the important area. You can explore develop the project concept and submit to the funding agency. That would be the promising field. Biosensors for detection of the environment pollutant, particularly those things are chances of getting the fund. And also the nanomaterials, again I told you, so nanomaterials can be using the carbon based or inorganic based or organic nanomaterials. These are all, and again these are all things you know very well. First 0D, first D material, nanomaterials, that all you are aware of, all of you are aware of it. And biomedical polymer application is a membrane, again diagnostic devices and vascular grafts, sensor, implants, scaffold, drug delivery. So here what we understand is that biopolymers are important and in a different field. And one more point I want to add here, food packaging. Food packaging. You might have seen that the Tetra Pak, there are some groups are working on that one. Again, that is also one aspect of for the project concept development. Biopolymer that will be coated inside the food packaging, and like a milk Tetra Pak inside the biopolymer layer will be coated. So that is a more advantage. Some of the biopolymer is acting as a anti bacterial. If you one more aspect, if you add a silver combination of the biopolymer and coat with the, that will be coated layer coating inside the Tetra Pak, and that can be act as a more antimicrobial activity. So silver is acting as a silver also is considered as a antimicrobial activity. Hope all of you following. Next, biopolymers in food packaging made from the renewable sources that I told you. So biodegradable, easily degradable, and based on the renewable sources, and it is from the biomass, source for the biomass. Microorganisms also produce the biopolymer, PHA, and polyhydroxy alkanates, and also using the biotechnology practice principles, polylactic acid, that also can be source from the renewable sources. Based on the petrochemical resources, these are all the not much easily biodegradable. This is synthetic chemicals. Now, as I mentioned, that biopolymer earlier I told you, the biopolymer combination with the silver nanoparticle, it can be acting as a antimicrobial activity that can be used for the fish and food packaging purpose and milk storage purpose, all these. So now you understood the importance of the biopolymer. And one more important aspect is that biopolymers are used in an electronic industry also. How this biopolymer will be helping electronic industry? As you know that there will be a PCB, printed circuit board. Printed circuit board, you know that the e-waste is how e-waste is affecting the environment. Lot of huge, millions of that, a million tons of the e-waste is generating. And also, it is very expensive to extract the metals from that PCB. So you have to spend more energy, more chemicals. Again, that will affect the environment. So that it is not a sustainable practice. And some of the group in I think I have mentioned here, Jiva and the University of Portsmouth in UK one group, research group has worked on the biopolymer that are used in the PCB, printed circuit board, with a biopolymer like a chitosan, all that. What is the advantage of that? But it is eco-friendly and easily degradable. And advantage of that, whatever the metals in that PCB, you know that all the metals will be there, and that metals easily extracted after this lifetime of this biopolymer. So and also it is a foldable, flexible also be there. So it is one of the good research area. So and also once it is lifetime is completed and easy to extract the metals in that PCBs. So that is the advantage. So some of the groups are focused on these areas nowadays. And one of the group in VTT or National Research Center in Finland also, they're working on the biopolymer application in the in electronic industry or PCB production. And biopolymers are sources of the renewable sources, and it can be used in a generator, it can be used in a solar cell, and it can be used a photovoltaic cells also can be used, and supercapacitor and display system also can be using, and also actuators, and also adhesives purpose also they are using, sensors already I told you, memory devices also using in the biopolymer. So instead of the synthetic chemicals that using in all these application aspects, and they are replacing with the biopolymers, obviously that practice is considered as a green chemistry practice. Sorry. The next one, biomaterials. This also is very important. Some of you are very much interested to involve in some research. Some of you can be focused on this area also. So biomaterials and biopolymers in the energy sector. Now you all of you know that how the battery waste can be effect on the environment. Lot. And if you consider the lead acid battery, so after lifetime gone, it throw into the environment or solid waste sites they are throwing, and that will be a very impact on the environment. So to avoid that, there are, again I'm not going to discuss more detail. There are two already it is here. Anode and cathode electrochemical cell is there now. One of the electrode can be made with the bio-cathode or bio-anode, using the even biofilm coating on the anode or on the cathode. You can generate the energy from that battery or electrochemical cell, and easily degradable that after lifetime war. So this is one of the important research area, and funding also will be more, and biomaterials and biopolymers used in the energy sector. Hope you understood that. And one more point I want to tell you is that the battery waste. Some of you always talking about we have to use the waste to useful product. Some of the group you can explore from the literature. Some I have mentioned here literature, and whatever the electrode they made in that battery, that material can be used for the removal of the pollutants, or use as a catalyst. But you can explore that also. Hope you understood. Once again, I'm repeating. So waste battery. One more thing I want to caution you, my dear colleagues, don't be directly break the battery. Very dangerous. I'm not suggesting you. Be careful if anybody want to do that, or don't allow the children also. So carefully, and by taking safety precautions, you can take the cathode material and anode material that can be used for as a catalyst, or the packing in the column for the removal of or adsorption, desorption of the pollutant. So there are some groups, some good papers or research groups are published. You can explore those things also. Now, one more aspect here, as I told you, plant biomass derived silica, carbon, and silica-carbon combination composite used as a bio-anode material for lithium-ion battery. So lithium-ion battery you know that is secondary battery. Secondary battery, you know that chargeable and also rechargeable battery. So anode is made with the plant biomass derived silica and combination of the copper. That will be coated on that will be the designing material for the anode in the lithium-ion battery. So it give a good efficiency, good electricity generating. So this is one example, plant biomass derived anode or cathode used in the battery system. So that we can call it as a bio-based battery, bio cathode or anode-based batteries. So these are the small, few methodologies. Cellulose, chitosan, lignin, these are all considered as biopolymers. Those are using in the energy materials, that's all. And also combination of the biopolymer and graphite synthesis from the catalytic graphitization, that also will be giving a more efficiency for anode electrodes designing. So you have to explore. So which gives a more porous nature, a more efficiency of the anode. So anode, you know that no, anode is a oxidation reaction, and the cathode reduction reaction is taking place. So anode electron generating more and received by the cathode, and the reduction takes place at the cathode, and the electricity will be generated. That all you know very well. So now the biohydrogen production. This is also one of the green electrochemistry method, chemistry method. Biohydrogen production by microbial electrolysis. And in this case, we have a anode and the cathode. And here in sulfate reducing bacteria, if you coat on the cathode electrode, this is a cathode and this will be the anode. At the cathode electrode, if you coat the biofilm, that means bacteria, which is considered as a sulfate reducing bacteria. So that will be acting as a production of the hydrogen. Now you can think this mechanism, but you have to isolate the bacteria, suitable bacteria from the source, or you can buy the bacterial culture from the bacterial bank. Even Imtech you can buy also from the. You can try with this mechanism. So, and also another advantage of this thing, you can use this method for the removal of the sulfate from the water. Sulfate from the water. Any industry which contributing the more sulfates, that like the fertilizer industry, you can use reduction of sulfates. So those things are involved in this one. So here and also you can get the byproducts also. When the sulfate is reducing to sulfide, and hydrogen also will be generated. So this is one mechanism that is considered as a green chemistry practice, biohydrogen production by microbial electrolysis. Microbial electrolysis. Like a micro fuel cell. And also one more aspect here, the electrocoagulation. Electrocoagulation is one of the green chemistry practice. You find the water containing more suspended particulate matter. So what they are doing in olden days, previous days, they are using what you call alum. Alum they are adding and coagulating, but itself is a toxic. Again, environmental impact. And after that, there is some studies are there. Nirmali seeds. There is a Nirmali seeds, that seeds available in the forest, some region, and they made it a powder after a little bit, fry, heated, and that powder they added and coagulating. That is also is a green practice we can consider, but efficiency will be very less that also. And here one more electrocoagulation is one practice. In that system consists of anode and the cathode, and one electrode is in many metal. Like you can take the iron as an electrode, and another one is inert electrode, well, like a platinum. And when the anode oxidation is taking place, and metal is M converted into Mn plus. So then the Mn plus enter into the water, and also hydrolysis of water is taking. When you provide the potential between the two electrode, suitable potential created between the two electrode from the external energy source, water will be ionized, and OH minus and H plus ion. This OH and M plus, Mn plus, and also OH minus, and it forms the metal hydroxide. This is. So that metal hydroxide is acting as a coagulant and flakes like and that will be attracted to the whatever the suspension in the water, and that will be settled. This is one good method. You can this type of technique can be used in a small water purifying purpose. You can think of it some small project, or you can introduce for the school children projects also. Very easy. And also same thing. Arsenic and fluoride removal also same mechanism. Same mechanism. This is one example. Removal of the arsenic and fluoride by electrocoagulation. Electrocoagulation. So this is also one green chemistry practice. So here, and one more thing, electrochemical process synthesis represent the green and advantageous alternative to the traditional synthetic process. So in using the catalyst, in presence of catalyst and some polymer, then again it produces the product. It forms the product without any waste. That is all. So these are the few examples for the anode material and also the cathode material. And also the Fenton reaction, electrochemical oxidation. This is all example of electrochemical oxidation. Is all these things. And Fenton reaction means, as you know that, and it produces the peroxide in the water. That is the formation of the peroxide in the water, and that is acting as an antimicrobial also. Photoelectrocatalysis also is one of the practice, green practice for the removal of the pollutant. Yeah, this is the microbial fuel cell. As an approach for the bioremediation of the pollutants. As I told you, you can have the two compartments, anode compartment and cathode compartment, and you can use this mechanism for the chemical oxygen demand water. This also example I am telling you for the small demo project for the student level. You can also guide them. And here in the STP sewage treatment plant, sorry, sewage treatment plant, the waste contains the lot of organic matter that is considered as a COD, and that water is sending to the anode compartment, and cathode electrode, as you know that anode oxidation is taking place and cathode reduction is taking place. When the organic matter present in the water, some metals also will be there, some biofilms also there. There, oxidation is taking place. When oxidation is taking place, the electrons will be generated from at the anode electrode, and that is flowed towards the cathode. So then electricity will be generated by reduction takes place at the anode. At the cathode. Reduction takes place at the cathode. Oxidation takes place at the anode in presence of the STP waste or C waste which contains the organic matter. Organic matter will be oxidized and it produces the CO2 and the H2O. At the cathode electrode, hydrogen will be evolved also. So these are the few examples for the reduction of the pollutants. That is a green practice I have mentioned here. And also it can be used for the, one more point I want to tell you is that, this also can be one important. And hypochlorous acid, you know that this can be used as a good green practice. You know that what is the purpose of the hypochlorous acid which can be used? As you know that the cleaning of the floor to eliminate any bacteria. Nowadays, many synthetic chemicals are there. Some companies are producing the plant origin products also will be released into the market. And this is one method. Even some of the company are manufacturing this device, and which produce the hypochlorous acid. Hypochlorous acid. If you take the two electrodes, anode and cathode, immersed into the salt water, which contain the sodium chloride, and if you create the potential between the two electrode, and that these are the reaction that takes place, and finally, very sorry. And these are the reaction takes place, and that at cathode, hypochlorous acid will be formed. So this is not a synthetic hypochlorous acid, and this can be used for the floor cleaner, cleaning the floor, or even biomedical devices. All can be cleaned with this one. And also there are some group are using the hypochlorous as a pesticide also. So this is one of the good green practice for the environmental protection. And also this is also dye-sensitized semiconductor system for a photocatalytic hydrogen production is also in future. This is another, and India also created a lot of fund for this research area. You can explore this area also. Some of you are already involved in the research. You can focus on this area also for the production of the green hydrogen using the semiconductors. Yeah. So these all, again, I'm not going to discuss much about it. And the biopolymers can be used in the health sector, wound healing and all the aspects. And also biopolymers are using in agriculture. Biopolymers are using agriculture and drug carrier, the fertilizer carriage, controlled dispersion of the fertilizer to the plant. This is one example, and that biopolymers are cellulose and all these things. And this is one of the good practice for the agriculture, for the sustainable practice. And also nano fertilizers, nano pesticides for the agriculture. And here the nano particle advantage of nano fertilizers and nano pesticide. Nano pesticides and nano fertilizer, nano pesticides. So based on the surface and based on the size of the particle, surface area is more, as you know very well, and there are different nanomaterials are there, first D, 0D and all that. And on the surface area of the nanomaterial accumulate the fertilizers and also pesticide. If you put that pesticide, that nano fertilizer and nano pesticide near to the plant, near to the plant root, and controlled release of the fertilizer will happen. So, and this is a good advantage nowadays. So even many research groups are focused on this one. Advantage of this one, you need not use the huge quantity of the fertilizer and pesticide. You know that how it is, how these pesticides are effect on the environment. So this is one of the good practice. So controlled release of the pesticide or fertilizer to the plant is a good practice. And also it suppresses the degradation of the pesticides also. And next one is the hydrogels, and exhibit the excellent performance in the adsorptive removal of the wide range of the aqueous contaminants, including the heavy metal removal, nutrients and all these things. And also hydrogels are using, this is also one good practice, used for the hydrogel tablets, like in the form of tablets. If you put it in the water, and whatever the contaminants in the water, that will be absorbed on. So, and also it can be used for the desalination purpose also. So this is one of the example. And also these hydrogels can be used, used for the agriculture purpose. If you put the hydrogels in the soil, and soil property is also increasing, and also the hydrogels hold the moisture a long time. Water holding capacity is more. So this is and also it suppresses the evaporation rate of the water from the soils. So this is also one of, and also it is a biodegradable. It doesn't affect the even soil bacteria or anything like pesticides. And this is also one of thing. Hydrogels are 3D cross-linked hydrophilic polymeric networked water adsorbent polymers, and it's a boom for the agriculture. And that polymers are the starch, cross-linked polysaccharides and all that. So as I mentioned, like a nano fertilizer and pesticide, similar to this, hydrogels also slowly releasing the chemicals or pesticides into to the plant. So waste is less and less consumption, that all will be expected from this process. And some synthesis process also. And one more point, last relating to the hydrogen, and it can be used for the desalination. As I mentioned earlier, hydrogels tablets can be added into the water, and all the impurities will be adsorbed on the hydrogels. It attracts it to that, and pure water will be left. So that is one practice. And also one more aspect here we should remember that, you can suggest, or again you can plan some project for the student, hydrogels for the desalination. And also nanofibrous hydrogel reduced graphene oxide membrane for effective solar driven interfacial evaporation and desalination. Yeah, this might you might have seen. Most of you have seen that this is a solar head still. So you can construct the area also is important. In this, you can coat with these hydrogels and carbon dioxide, what is called graphene oxide combination, and it absorbs the more light. And evaporation rate, if you put that hydrogel combination graphene oxide, put into this solar still, then sunlight will be enter through the glass, and evaporation rate will be more, and you can get the pure water. So you can remote area there, place where you don't find good clean water, I mean more salty nature, you can suggest this type of. And also this is a floating the nanofibrous hydrogels also can be made this is one of the good practice for the desalination process, and also produce the pure water. And the same thing, some group are working, this is a group, if you want to go through more literature, more detail about this, you can go through these references. And the hydrogels can be used for the production of the desalination from the salt water, from the sea. So this is about one example. Biopesticides, and most of you are aware of that. Pesticide causing a lot of impact on the environment, and also human non-target organism. And so that led to the development of the biopesticide. Biopesticides are also having the pesticidal and insecticidal characteristics that can be isolated from fungicide, bioherbicides, and these are the examples. Some of the example already produced, I mean, available in the market. Also, some companies are manufacturing. Even example, neem. Most of you know that, no? Neem is also one of the example of the biopesticides. So again, the combination of the biopesticide and nanotechnology, again, that will be more effective in the agriculture field. So that is about the biopesticide. Green analytical chemistry technology in IoT based smart farming. Even you might what you call smart building. You might have seen that smart buildings. That means the energy of less consumption, solar energy used in that house, no waste of the energy, and good material using for the construction. And some of the material walls also emit the radiations. So using the good soil for the bricks and making, that will not affect the any causing the environment effect. That will not cause any environmental impact. So this is one example. IoT based smart farming, I told you earlier, there are some sensors. I think these all many research papers are there. Again, you can go for some of the projects for the students also. Using the maybe 200-300 cost of this sensor, you can connect to the using the IoT tool. You can monitor the real-time monitoring of the water quality, dissolved oxygen and all that. Even aquaculture also can be. So if the water, and one more point I want to add here, you might have seen that many places, maybe in Andhra or many cities have the drinking water system. So what is the mechanism there? Membrane technology and also the ion exchange process. So this is inlet water and the outlet water. Here they set the TDS meter. This is 200-300 cost sensor. They put the sensor, and this by using the IoT, you can get the data of the outlet water. What is the dissolved oxygen? What is the total dissolved solid? Means hardness. If the hardness is more, so the efficiency of this device is less. So you can monitor, and if the automatically it will switch off this device. So that type of things are there. So that all will be IoT based smart farming solution, or even a drinking water system can be also. So there are again you all these things. You all of you know this. Pesticides are spraying using the drones and all those things. This is also, and there is one more study, hydroponic practice. So you can produce without using the soil, but quality of the water is very important. 6.5 pH should be maintained in that hydroponic channel. Then the growth will be more, and also you should recycle all the time. So that all pH of the that water should be monitored online or real time using sensors. So this is all one example for the green. These are all the green practice, green chemistry practice. So organic farming, that all you know very well. So this is the bio-based surfactants, as I already told you. Some of the plant extracts are considered as a surfactant, and alkyl polyglucoside, alkyl benzene sulfonates also as a isolated from the natural source, acting as a surfactant, sulfonins and all that. Oh, sorry. Oh, sorry, slide are not changing. Sorry. So this is the catalyst and biocatalyst. Already we have seen some example. This is one example. The bacteria. This is one example for the green analytical chemistry for the environmental analysis and all that. One example here I have taken. I'm going to explain that bacteria-based silver nanoparticles. So there are reducing agent. You can use the sodium borohydrate and the citric acid, ascorbic acid, that all used for the involved in the chemical synthesis. And again, there will be some of the impurities that reducing agent will be accumulated on the that silver particle. Again, that will be effect on the where whatever the purpose application you use for the silver nanoparticle, that will be involved, that will be interfering. But if you use the bacteria based or the plant extract based green synthesis practice for the synthesis of the nanomaterial, will be more effect as a catalyst. That is also one of the green chemistry practice. Just I have mentioned here. So simply you can take the silver nitrate salt and known concentration, that also you should maintain, and temperature, and put into the reactor, small reactor, and also along with the plant extract, water extract, not the solvent extract, not methanol extract. We can plan in your at work, your institute also, and it synthesize the nanoparticle. You can take the different plant extracts. Before start the plant extract, you have to refer the literature. Which plant is not studied much, then only you start. Nowadays, many people are reported that. So you have to explore. That is one itself is one what you call habit or practice. How do you find out that this plant has not been studied for the synthesis of the green synthesis of silver nanoparticle? You have to do the literature survey. You can go Google Scholar, all that you can find out. So those plants are not studied, then you can use that plant. That will give a weightage for our study. That is, and characterization by following the SEM and all that you know very well for characterization. After that, you can use that catalyst for the degradation purpose and all, or you can use as a detection of the pesticide also. Even carbon quantum dots, carbon quantum dots, silver nanoparticle, you can synthesize following the green practice, and that will use for the you can develop the sensors also with that carbon quantum dot, and also using those silver nanoparticle as a surface enhanced Raman spectrum. I think we have one slide of that. That is also good practice. So you need not use the much time for the extraction of the compounds from the water or any sample matrix. So little sample is sufficient. So those are all the green analytical practice for the environmental sample. So this is one. Here it is one thing. I hope I have some more time. I can give me some more time. I can finish the whatever I planned. Silver nanoparticles for the CERS for the pesticide analysis. Now, silver nanoparticle, how to synthesize, I told earlier slide. And CERS is the surface enhanced Raman spectrometer. As you know that pesticides are very present in the contaminator, very, very low concentration, even a nanogram or microgram level. So that will also be affect the human. Even milk also be containing the pesticide. So detection is very important. So, and that low level concentration can't be detected by the small, some devices like HPLC or the GCMS and all that. So there is one method for the Raman spectrometer by following the sample treatment, surface enhanced Raman spectrum method, and where the silver particles will be treated with the water sample or milk, whatever the, and or the human bovine serum, albumin, and all the pesticide will be accumulated on the surface of the silver nanoparticle. So when you subjected the that material for the Raman spectrometry, signal will be enhanced. So earlier, without Raman silver nanoparticle as a source, and the signal will be very less. And for that, you can use the some solvent extraction method for the extraction of pesticide from the water. So now if you use this method, so the particles, small sample is sufficient to detect the pesticide in the water. So when that pesticide is coated on the surface of the nanoparticle, that signal intensity will be more. So you can detect even at the lower concentration. This is very good area, the promising research field for the detection of the pollutants from the water, and it considered as an environmental sample analysis. So that is about one example. I feel it is good to discuss. And also one more thing, analytical spongy nickel organic photocatalyst, converting the, this is one important aspect. So carbon dioxide is a more greenhouse gases and it affects the environment also, and climate change because of this one. And this, to reduce this one, using the nickel organic photocatalyst is metal organic FOM, metal organic frameworks, metal combination and organic molecule. So that photocatalyst is converting the CO2 and converting into the ethanol fuel. There are some groups working on this conversion of the carbon dioxide which contributing from the industry, that converted into the ethanol. Ethanol is as a fuel. It's like a biofuel. So that is one of the practice for the conversion of the greenhouse gases converted into the useful product of that fuel. That is one example of that. And also in this one, photochemistry, electrochemistry also can be used. Even photocathode or photoanode, or a combination of the photocathode and photoanode combination of these electrochemical cell, and CO2 will be converted into the ethanol or the acetic acid or the formic acid. So this is one example that considered as a green electrical. And CO2, and this is also the same mechanism. And this is one example important. Most of you are aware of this, I think. And most of the research inventions are takes place based on the nature-inspired research. Even if you take the CV Raman, or even you take the bullet train, and all these are originated by observing the nature. So this is one of the example who can consider as a nature-inspired invention. So as you know that the plant natural photosynthesis, how it happened, CO2 and moisture, and that will be converted in by taking the energy from the sun, and it will be converted into the sugars for the plant growth. And similarly, mechanism applied here, artificial photosynthesis.
Sir?
Artificial.
Excuse me,
Yes.
sir.
Madam.
Next, sir is ready for the session, sir. That's
Okay.
Please
Just
hurry up, sir.
I'm going to conclude. Let me have 5 minutes. Is it okay?
Okay, sir. Okay. No problem.
Thank you. So this is the one of the artificial photosynthesis for the conversion of the CO2 into useful product like methanol. So that is one. This is one catalyst for the industry, natural catalyst. This is one example for the application of the water purification, desalination, and also and aquaculture. Sorry, it's not changing fast. So this is the photocatalytic reactor for water purification. I think you have the slide. You can go ahead with that. In the reactor, catalyst will be there, and polymer also will be there, and that will enhance the degradation of the pesticides or other components. So this is another biocatalytic remediation of industrial pollutant for the sustainable. So this is one example, and also the plant-mediated photocatalysis and only plant material, and green analytical method, ionic liquids, amphiphilic solvents, and deep eutectic solvents as a green solvent, and green green chromatography. I thought of giving more detail about this, but anyway, bioremediation, biotechnology, environmental biotechnology also is one of the good practice in the green chemistry, using bacteria and even groundwater contamination, eliminating by using the bacteria. And these are all some of things. And this is one of the plastic. Yeah. So waste to energy. Only 5 minutes. Waste to the energy conversion. Plastic converting photo reforming of the plastic in presence of the alkali and the plastic that converted into the byproducts, useful product. That is good one aspect. Yeah. So that is last one. Yeah, this is one of the method, green method for the extraction of the pollutant. Solid phase SPE method for the less solvent, SPE method for the less solvent requirement for the extraction of pollutant from the water instead of the column chromatography or the solvent extraction method. So this is HPLC method is also considered as a green chromatography, which where you can use the green solvent. And yeah, this is method finally. Yeah, summary. We have discussed about this. About the principles of innovation, principles and innovation methods in green chemistry and green analytical chemistry, those important role of shaping the sustainable future. We have highlighted the selected research findings, MCR, catalysis, and all those things. And finally, take-home message: the green chemistry and green analytical innovations are essential for the advancing sustainable practice across all engineering and science research and industry. The collaboration is important nowadays. So you can productive data you can produce. The research in a green chemistry is a promising research area. Keep updating about the latest advancement in green technology. Actively participating in discussion and participating in the conferences for driving continued progress in a green chemistry. I encourage each one of you to involve in a research that pave the way for a sustainable and environmental friendly future. Thank you for your attention during the presentation. Sorry, I took a lot of time.
No problem, sir. No problem.
Excuse me for that.
Thank you, sir, sorry for the disturbance, sir.
No. I cannot. I should follow some. Yeah.
So thank you, sir, Dr. Srinivas Rao garu Ammaneni, for the inspiring and thought-provoking information regarding your topic, green analytical chemistry approaches on environmental analysis and sustainable development. Thank you, sir. Your lecture is excellent, focused on especially on green chemistry and sustainable development.
Permit me just 10 seconds, and dear colleagues and respected teachers, all of you, you are the role models for the, for the young children. And any doubt, anything relating if these aspects or research or anything, whatever, if I know, I can share to you. You have my email ID. You can always contact me through email ID. So what I can give you some good inputs, even project development or when you are submitting the funding application, I can guide something. So this is
give
my
your mail ID, sir.
Already in the first slide it is there, ma.
Okay, sir. Okay, no problem. I will share the mail ID.
And also, Madam Nirmala, Madam Ji, you can share this PPT. And also one protocol I have told I didn't get time. I need more time actually. That HPLC demo and protocol discussion. And please share this PPT and that pharmaceutical analysis by HPLC protocol. I share to you and share to all of them.
Sure, I will share the.
Finally, namaskar to everyone. Yeah.
Thank you, sir. Thank you for your wonderful session.
Thank you. Hoping. Thank you.
Now
Thank you all.
Okay, thank you, sir. Now let us proceed to the next talk of the session from an eminent personality of international reputation, Dr. Akhilesh Kumar, Professor Special Appointment, EY Women's University, Seoul, South Korea. Now I request Dr. V. Sumalata, Assistant Professor, Department of Chemistry. Today's eminent speaker, Dr. Akhilesh Kumar, Professor for Special Appointment, EY Women's University, Seoul, South Korea.
A very good afternoon to all. I am Dr. V. Sumalata, Assistant Professor in the Department of Chemistry. It's my great pleasure to introduce our distinguished speaker, Dr. Akhilesh Kumar, who currently serves as Professor for Special Appointment at EWHA Women's University in Seoul, South Korea. With a research career spanning several years and marked by significant contributions to the field of biomimetic chemistry, He is a leading expert in the study of high-valent mononuclear and binuclear metal complexes and their role in mimicking the behavior of metalloenzymes in biological systems. Dr. Akhilesh Kumar has a rich academic background, having completed his postdoctoral research under the esteemed guidance of Professor Unbu Nam at EWHA Women's University. His work focused on the complex yet fascinating world of mimetic metal oxygen intermediates and their role in dioxygen activation reactions. His doctoral research centered around bio-inspired coordination chemistry associated with Professor R.N. Mukherjee at the Indian Institute of Technology, Kanpur. And he holds both bachelor's and master's degree in chemistry from Chhatrapati Sahuji Maharaj University, Kanpur, India. As a prolific researcher and innovator, Dr. Akhilesh Kumar holds 5 patents, 3 provisional patents, and has published more than 20 publications in internationally peer-reviewed journals. And he attended and presented papers in more than 7 national and international conferences. He has been recognized with numerous awards and certifications, including the prestigious Natural Science and Engineering Research Council of Canada NSERC Postdoctoral Fellowship Award from the Government of Canada, the SABEX Innovation Challenge Award, and DuPont's Lean Six Sigma Black Belt certification. Now, Dr. Akhilesh Kumar will share his recent trends and insight on the synthesis, characterization, and reactivity of metal oxygen complexes, shedding light on how these findings could impact our understanding of biological processes and contribute to development of new biomimetic reactions. Thank you. Ma-
I request Dr. Akhilesh Kumar to deliver the lecture. Sir, not audible, sir. Not audible. Please unmute, sir.
Am I audible now?
Yes, sir. Yes, sir. Okay, carry on, sir.
Yes.
Okay. Thank you very much for the invitation.
Sorry,
for
for the late.
Yeah, it's okay. Yeah, we actually in here, I have again meeting around 5:30. So as you people told me to at 4 o'clock we have to start. So it's okay, no problem.
Sorry.
So thank you very much for giving me the opportunity to present my work here. Thank you very much for all the organization committee for wonderful webinar. So you can see here then the first slide, this is my university, Eva Women's University in Seoul. So today I will discuss my recent work related to the metal oxygen chemistry. So here for the metal oxygen intermediate in dioxygen activation and formation chemistry. So as we know, the oxygen is very important for the life. So why, if it is oxygen is very important, what is the role and how it reacts with many enzymes and what kind of catalytic activity is there and biomimetic type of activity, which all things we have to cover in this talk, but I will not show all in detailed way. So I will show some short part and try to complete all the things. So in the oxygen, so oxygen is the essential for life process. So we know that the oxygen can reduce in the superoxo and the peroxo and after that H2O2 and this water. So one primary goal in the biometric research to understand the active site of the intermediate when metal bind with the oxygen and what kind of structural change is there, what kind of electron transfer reaction is there, and according to this, which kind of intermediate is formed and which was applicable in many biomimic enzymatic reactions. So as we know, I will show here for the some intermediates as we can show in the when oxygen react with the metal center. So first is the one electron oxidation of metal and then convert to the superoxide species. That superoxide species can undergo the react with another metal ion and convert to the dinuclear species. If it is not dinuclear species, it takes proton and hydrogen atom, it convert to the hydroperoxide species. That hydroperoxide species by the OO bond cleavage, it converted to the oxo species. So now, so why, which kind of intermediate possible with the oxygen and which kind of enzymes are present which having this kind of intermediate? So as we know, we started with the reduced metals. So suppose we have iron, manganese and cobalt, nickel, many metals. So generally for the biomimetic study, manganese and iron we studied more. So metal 2, that means the reduced metal center react with the oxygen to form with a metal 3 superoxide species. So that means metal is oxidized and one electron goes to the oxygen center and it converts to the superoxide species. That superoxide species again react with the metal 2, that is the metal 2 oxidation state and convert to the superoxide species. And that superoxide species are main intermediate for the methane monooxidase. I will tell you the next slide. That peroxide species by the OO bond cleavage, it convert to the terminal oxide species. And the another method is if superoxide species is formed, after that it take again one electron and convert to the peroxide species. Another possibility is directly we add some oxygen transfer agents such as soluble PHIO, MCPBA, sodium periodate. This kind of oxygen atom transfer agent, it directly converts to the metal oxide species. And another green oxidant are also available like H2O2. If we directly use base and H2O2, then again these peroxide species are generated when depend on the potential of the metal center. And this peroxide species by adding the proton, it converted to the hydroperoxide species. Now question is that these kind of species are present in many biological reactions such as, I will tell you here. So one is the metal superoxide intermediate oxy PHM enzyme and the extradiol dioxygenase. In case you can see in the copper 2 center bound with the superoxide species. Another is the extradiol dioxygenase enzyme in which the iron 3 center bind with the superoxide species. And this PHM is widely distributed in the plant and the animal kingdom and catalyze the C-terminal of amidation and glycine extended propeptide. Another one is the extradiol dioxygenase. So we initiate the catalysis of ring cleavage for this benzene ring cleavage and reaction through the bidentate binding of catechol and substrate to the ferrous iron active site. Another enzyme is the metal hydroperoxide intermediate. As we know, the reversible dioxygen binding in invertebrate, that is the hemerythrin. So hemerythrin, the iron 3 dinuclear iron 3 center is there in which this hydroperoxide type of moiety bind with the hemerythrin. So hemerythrin found in the invertebrates like mollusk and all the things. And another one is the hemocyanin having the copper in which also the peroxide binding with the copper 2 center. And that is also the related to the blood in the human, that is the because of the iron the color is the blood is red, but in this case arthropods that color is for the blue because of the copper center. Another thing, another high valent metal oxide species also available, that is the non-hemmed iron hydroxylase. This kind of key intermediate responsible for the methane monooxygenase. And another one is alpha ketoglutarate dependent iron dioxygenase, that is responsible for the cell metabolism and physiology. So here another thing, as we know for the photosystem 2. So photosystem 2, it take oxygen and then it take water and convert to the oxygen. But how it's possible? So as we know for here is a tetranuclear magnetic center is present. In tetranuclear magnetic centers in which 3 manganese present in the 3 oxidation state and another is the 4 oxidation state. When again with presence of light, that S0 state convert to the S1 state, that means 1 manganese 3 oxidized to manganese 4, that means 2 manganese 3 and 2 manganese 4 moiety. And then again with presence of light, this convert to the S2 state and S3 state, and finally the S4 state. The S4 state is very crucial. I have shown here that is the X4 state in which one metal ion bind with the manganese 5-oxo species, and that 5-oxo species, and this is the calcium bind water, and that water attack on the nucleophilic type of reaction and convert it to the oxygen. So that means the water convert to the oxygen by the photosystem 2 using this enzyme. Another one is the methane monoxygenase. So as we know, methane is a greenhouse gas. That's how. So because of that greenhouse effect, nature also choose like some enzyme. That enzyme at room temperature convert methane to methanol. So methane, as we know, with a BD bond dissociation energy is very high, around 105 kilocalorie per mole, and with presence of oxygen, that methane convert to the methanol. So same type of reaction is here, that a reduced form of Rn2 center, and this reduced form of Rn2 center binding with the Rn2 interaction, that is the B, and another one when it interact with both Rn2, it gives 2 electron to the oxygen, and that oxygen convert to the peroxide form, and that peroxide form by the OO bond cleavage convert to the Rn4 bisoxo, and this is the Q form. We presented here, this is the Q form, and this is Q form for responsible for the methane. Another one for the same kind of species, that is the human deoxyhydroxine hydroxylase. This is the enzyme where the peroxo binding with the Rn3 center, and this peroxo binded Rn3 center for responsible for the cell proliferation. So now we understand that we know that oxygen bind with the metal center, but first question is that when oxygen bind with the metal center, what is the state of that? How it react with this system? So we can say in the Pauling, first Pauling represent that the Rn2 state directly bind with the oxygen. So in which Rn2 is S equal 0 and oxygen is also S equal 0. But this is not proved by the Mosber and the magnesium and resonance Raman. So this is structure after some time we can say that this is not the real structure. Another one structure is McLaren Goddard. They give the structure in which the Rn2 is S equal 1 and oxygen also S equal 1. Then Rn state with Rn2 state and oxygen binding this fashion. And this is also not the correct one structure. And finally, we propose the final structure in which we suggested the Rn3, that is S equal half, bind with the oxygen with superoxo fashion. So that means the oxygen first interact with the metal center, and that metal center give 1 electron to the oxygen and convert to the superoxo species. So now this model proposed, and after that proved that Mosber study have supported this Weiss model, and Weiss model also supported with a resonance Raman spectroscopy. And now the another thing is the catalytic cycle of cytochrome P450. In the cytochrome P450, we can also see that the Rn2 center is there, and again it reacts with the oxygen to form a first Rn3 superoxo species that is responsible for the oxygen transportage and the storage in hemoglobin and the myoglobin. And this ferric superoxo species with presence of proton and electron convert to the Rn3 hydroperoxo or peroxo species that is known as the compound 0. And that compound 0 is responsible for the substrate oxidation, and with presence of acid, this convert to the Rn4 oxo cation radical species. That cation radical be known as the compound 1. That compound 1, this is also called the compound, if it is not cation radical, directly the Rn4 oxo species is also responsible and take electron. If we take this O bond cleavage here, and this convert to Rn4 hydroxo species also. And that hydroxo species with presence of proton and electron convert to the Rn3 species, and the catalytic cycle again starts. So now people first focus how this Rn4 oxo is responsible for different kind of reactivity. So here, so people in the Science 2010, Professor Green published the science paper. They suggested that the porphyrin 3 complex cation radical with presence of oxidant, this convert to the Rn4 oxo species, and cation radical, that is the formally 5 oxo species. That 4 oxo cation radical species are responsible for the many oxidation reactions such as the alkene hydroxylation, alkene epoxidation, and sulfur oxidation. And another the enzyme is the alpha ketoglutarate dependent enzyme tau D, in which you can see there the taurine dioxygenase is Rn2 center, and this oxygen again this Rn3 superoxide species, that Rn3 superoxide species binding with carbon center, and this carbon center then this cleavage of O bond is converted to the Rn4 oxo, and this is acetate type of binding, and this acetate type take 4 hydrogen from this taurine and converted to Rn3 hydroxyl species and the radical on the taurine, and this radical is converted to Rn2 and this taurine oxidant. So this is the enzyme for the alpha ketoglutarate dependent tau D enzyme. So now after that people mimicking this kind of system. So first in 2003 Professor Nam and Q first published the Rn4 oxo crystal with the non-heme enzyme. They using the TMC ligand, and the TMC ligand adding the PHIO as an oxidant, and they found that the Rn4 oxo species are generated. This Rn4 oxo species are characterized with the many various spectroscopy and also the crystal structure, and the crystal structure suggested that the Rn oxygen bond length is 1.6 angstrom. That suggested yes, this is the Rn binded with oxygen with double bond. And after this discovery, many people are using different kind of ligand and published more than 90 non-heme Rn oxo species are available, and they are showing different kind of reactivity, such as you can say if we have the Rn4 oxo species, you can do different CH activation, you can do the alkyl aromatic oxidation, alcohol oxidation, and dealkylation reaction, you can do the alkene epoxidation reaction, para oxidation, that is phosphorus oxidation, sulfur oxidation, and aromatic ring hydroxylation in this species. So nowadays these 4 oxo species are too much available, and people are not focusing on nowadays on this species. Now people focus on different type of species. Here we can say Rn3 hydroperoxide species. What is the potential of this? Why people some different enzyme using this kind of hydroperoxide or some alkoxo type of species are there. So after that, all these reaction, people in our lab, we are working out 12 TMC, 13, 14 and 15 TMC and using the different kind of metals and generate different species like a superoxo and a peroxo species. So now in this case, we can see that 14, 13 and 12, we publish many papers with using this kind of ligand such as chromium, we publish the superoxo, in the manganese case peroxo, iron case also peroxo, with cobalt, nickel superoxo as well as peroxo, and 13 case we are progressing on the chromium case, but manganese and jags and the iron and cobalt nickel with suppose that this is the peroxo species and show different kind of reactivity with this kind of species. So after that, Professor von Moonem first they generate the peroxo species in 2011, and they published this result in the Nature, and they suggested that in the cytochrome P450 there is a hydroperoxo or peroxo species are there. What kind of bonding is there? What is the bond length, and what kind of reactivity they propose? So here they propose got the structure for this peroxo species, and here oxygen and oxygen bond length we can say 1.463 angstrom, and Rn oxygen bond length is 1.90 angstrom. And they also did the resonance Raman data, suggested that oxygen stretching frequency is 825 nanometer. This is for the O bonding frequency, and the Rn oxygen, this is the Rn oxygen stretching frequency is 485 nanometer. When they using the 18O labeled species, they 825 nanometer 6 centimeter is convert to the 784 according to Hooke's law. We can confirm that here there is a 2 oxygen present there. And after that, what happened to if peroxo species are there? Then what happened if we added acid there? So if we added acid, this is our peroxo species at 877 nanometer bands for the peroxo species. When we added acid, that is a perchloric acid or HOTF, then this peroxo species convert to the hydroperoxo species, and that hydroperoxo species band at 520 nanometer. And after that, this hydroperoxo species breaking off this O bond and converted to the Rn4 oxo species. Same kind of cycle you have seen is the cytochrome P450, and we use the solvent at acetone and OTF at minus 40 degrees centigrade. We generated this kind of species. So now we have the peroxide species as well as the hydroperoxide species and as well as iron 4 oxide species. So all these species follow the cytochrome P450 type of catalytic cycle. And now the question is that, okay, we have the great characterization of this species. Now, which kind of reactivity can we use this kind of complex as a catalysis or some reactivity study? So yes, we know that if we use hydroperoxo and oxo species, generally these hydroperoxo species or oxo species shows the electrophilic reaction. For the oxo, most oxo species shows the electrophilic reaction. But if we use the peroxo species, that peroxo species shows the nucleophilic reaction. But in case of 14 TMC hydroperoxo species, it shows ambiphilic reactivity. That means we can show here electrophilic as well as the nucleophilic species. And now the question is why? Why it is so different kind of reactivity? So now people thinking that first that hydroperoxide species, this is the nucleophilic and as well as the electrophilic deformylation reaction is reported. But if we using the peroxide species, in the peroxide species it shows only the nucleophilic species. So people believing that okay, this nucleophilic species, nucleophilic reaction shows because of oxygen having the sufficient electron density, that are because of the peroxide species, and that peroxide species attack on the electrophilic center, and then because that's why it shows the nucleophilic reaction. Then after that we have to understand why it's happened. Then we prepared another system here. So we are using the RN213 TMC species and generate the RN2 complex, and after that this is the crystal structure of the RN2 center. And when we added H2O2 as a green catalyst here and generate the peroxide species, and after that we characterize by the CSIMS, that we can say here for the when we use H216O2, then the peak at 330.1. When we change 16 to 18 O2, that 330.1 converts to the 334.1. That means it suggested that our species having 2 oxygen atoms are incorporated. And this is the intermediate generated at minus 20 degrees centigrade in the TFE. And after that, we check the reactivity of this peroxo. Then interestingly, these oxo species are very reactive toward the electrophilic reaction. You can see here, this thioanisole and the alkane oxidation happen here. So we are using that sulfoxidation reaction. When you added thioanisole in this reaction, you can see within the 300 seconds the reaction is complete. If you are using dihydroanthracene, the CH activation within the 1000 seconds, the reaction is also complete. When we do the kinetics and all the reaction for this, we can get the Ki is 5.8. That suggested as there is a hydrogen atom abstraction reaction is there. When we replace the hydrogen atom with a deuterium, then we got the Ki is 5.8. And also we can different xanthine, dihydroanthracene, CH3, we got the different kind of slope, that is the negative value. In the case of sulfoxidation, we are using also thioanisole. If we replace thioanisole with a para position like methoxy, methyl hydrogen chloride and NO2, we also see the slope at minus 0.61. These kind of reactions are electrophilic reactions. So now people were thinking previously the peroxide species are the nucleophile, but it is not true. The peroxide species also has a electrophilic reaction. And another thing is that, okay, so there are different kind of oxygenase reactions happen. So I divided the oxygenase into 2 parts. First part is a monooxygenase and another part is a dioxygenase. In the monooxygenase, we can say that only one oxygen incorporated to your substrate, that is a monooxygenase type of reaction. If you incorporate 2 oxygen to your substrate, that is a dioxygenase reaction. So in 2003, that is a very famous iron 4 oxide species. They suggested the monooxygenase type of reaction, that means one oxygen incorporated to the substrate. But now we are focusing on that, okay, what happens, how we can go 2 oxygen atoms incorporated in the substrate. So here some enzymes are there. Then tau D enzyme, in the starting I shown there is a RN2 center, and this RN2 center react with oxygen to form a superoxo, and this superoxo bind with a carbon atom here and release the CO2 and form a iron 4 oxide species. That iron 4 oxo species reacts with a substrate that is alkane and converts it to the radical, and radical is a rebound to form a ROH. That means we can see here only one oxygen atom is incorporated to the substrate. But the another species is dioxygenase. In the dioxygenase, you can see iron-2 species react with oxygen with presence of proton. It converts to the hydroperoxide species, and this hydroperoxide species form a intermediate that is 5-oxo-hydroxo species. And that 5-hydroxo species react with the naphthalene, and it converted to the adduct and finally give the diol product. So in this case, you can see there is a 2 oxygen atom incorporated with a substrate. So that means this naphthalene dioxygenase, because as we suggested the name is a dioxygenase, the naphthalene shows the 2 oxygen incorporated. So now in our system also we tried with using, so Professor Ramaswamy first published the naphthalene. Can we turn off the mic? I have too much noise is there.
Yes, sir. Yes, sir. I already informed, sir.
Oh. So in the Professor Ramaswamy first published that the iron-2 center react with the oxygen and it converts, you can see the peroxide species is transferred, and that peroxide species directly bind with a naphthalene to form a diol species. They have the crystal structure of that. In 2003 they published in the Science. And the another possibility for this, people also propose that if you have the iron-2 center, first oxygen with proton, this converted to the iron-3 hydroperoxide species, and that iron-3 hydroperoxide species O bond cleavage, and this convert to the iron-5 oxo-hydroxide species, and when you have having the alkene or naphthalene, and that substrate converted to the diol species. Then after that we also prepare that iron-12 TMC, and with using the green catalyst with presence of base, the peroxide species is formed, and that peroxide species will react with the alkene. First it bind with the their metal center, and after that in this case we are using styrene, and here we are using the cyclooctane. In the both case you can see the cis fashion of binding with the this alkenes, and finally when we added the acid here, then diol is formed as we shown in the nature in the naphthalene dioxygenase species. We published this paper in the JAX 2023. And here I will tell you the detailed story of this intermediate, why, how it generate, and how, why it show the dioxygenase type of reactivity here. So first, this is the, we have to prepare the starting material, that is Rn2 center, and after that we have to show the reaction. So here we are using the 12 TMC ligand. So 12 TMC ligand, we using the RNOTF system, the salt with presence of argon, it converted to the Rn2 center, binded with, coordinated with 2 acetonitrile molecules. When we characterize this ESIMS, then we can say there is a 2 peak at 433 and 162 for the Rn2 center, and this is the EPR spectrum. This suggested that Rn2 is silent because of the even number of electrons, D6. And after that we generate the intermediate with this Rn12 TMC species with using the H2O2. We can see the H2O2 when we generate the peroxide species is formed at minus 60 degrees centigrade, 670 nanometer peak for the your peroxide species, and this is the EPR that suggested that this is the Rn3 high spin peroxide species. When we try to optimize the structure of this, that optimize the structure shows that the oxygen-oxygen bond length is 1.38, that is comes out of the region of peroxo moiety, and here is the natural decay at more than 15,000 it will take to complete the reaction. And after that we also check the Mossberg measurement of the complex 1. For the Mossberg measurement, the S equal 5 by 2 and the delta value is 0.52 mm per second. These all the values suggested that yes, this is the our Rn is +3 oxidation state, and the quadrupole splitting and isomer state both are in the same range. And the X-ray absorption spine structure for the data of 1, that is 1 for the peroxide species, was best with, we can say here there is a 1 electron oxidation that suggested yes, our Rn2 converted to the Rn3 center. And after that we perform the resonance Raman of complex 1. In the resonance Raman of complex 1, the 7 lambda max excitation wavelength is 780 nanometer, And we can see here the peak at 808 and 755. 808 when we using the 16 of H2O2, and this shifted to 754 centimeter inverse because of adding 18O. And here is the DFT optimized structure proved by the Fraser instrument. And after that we perform the reactivity with system with using the alkene. So here when we using the styrene, so styrene when we added at the natural decay we know it will take 15,000 seconds, but when we added the styrene that convert easily decays within the 1,000 seconds. When we check the using the styrene in place of we are using the styrene D8, that means the deuterated one styrene, and here is the hydrogen in place of deuterium. Then we got the Ki is when. That Ki suggested that there is a no hydrogen atom abstraction is there. Directly C double bond attack on that peroxide species. And after that, when we added this system, styrene to the peroxide species, and we found the ESIMS. And ESIMS is only one peak, that is 420.1. This 420.1 because of the adduct of this complex. This when we using 18O2 with place of the 16, there is a 4 unit shift. That 4 unit shift suggested yes. Therefore, there is a peroxide unit that binds with the styrene center. And here is the crystal structure of the styrene center. And after that, we also perform the MOSFER and EPR. The EPR also shows the G value 6.92, 5.02, and 1.9. There is the iron 3 high spin center of the system, and the isomer shift is 0.46 and quadrupole splitting is 0.83. It's also favorable for the iron 3 center. And after that, we using the different kind of alkenes like chloroalkene, using the para position, and chloride for the meta position, and chloride nitro for the para position, and we perform the kinetics reaction with there. And after kinetic reaction, we also perform the CSIMS for this species using chloro for the para position, chloro for the meta position, and para position nitro. In all these cases, we can see some adductive form every case. In the chloro case also 554.1. In this case, for the meta we are using also 554 point, but we are using the nitro one that shifted to 465.2. And after that, we perform the check the reaction for this, and you can see using the different derivative like nitro, chloro, parachloro, metachloro, and simple hydrogen, the rho value is plus 0.46. That suggested yes, your peroxo behave like a nucleophile toward the styrene and the styrene in this case. So here is also we apply the potential in electrode potential for the substrate, and after that we also check the kinetics reaction with log K2 plot, and also got the slope plus 0.74. This proved that our peroxo species in this case behave like a nucleophile. And we also use the H2O 18 oxygen label. So some people suggested that maybe this is not peroxo. During the reaction condition, maybe O bond cleavage is happen, and after that reaction will be there. But if it is O bond cleavage is there, when we added the oxygen, that 16 should be changed to the 18 one. But we could not see any change. That means there is no O bond cleavage is there. That peroxo species directly react with our alkenes. And after that, we perform many reactions using the different kind of system. So we can first in this case, when we using the H2O18 label, there is no exchange of 18-18 and 16-18. That suggested that there is a no OO bond cleavage of this peroxide species. Another one, we are using the H2O16O2 and H2O18 1:1 condition. In this 1:1 condition, we found there is no exchange of 16O and 18. This studies prove that also there is no exchange for OO bond cleavage. Another one, we are using the iron 57 isotope and iron 56 isotope using the 16O2 and using the 18O2. If there is an exchange, it should be 16-16 and 18-18, but we could not get 16-16 and 18-18. That's also proof that whatever oxygen comes, this is directly involved with the peroxo. There is no O bond cleavage happen here. And after that, we change the reaction with the cyclohexene. So So for the cyclohexene, we can say using the all hydrogens here, and when we replace hydrogen to the deuterium, when we also get the Ki is 1. That Ki also suggested that yes, our reaction, there is no hydrogen atom transfer there, that double bond directly react with the peroxo species as a nucleophilic fashion. And we also did reaction with the cycloheptene, and the cycloheptene also shows the reaction, and also the cyclooctene with the kinetics reaction. And after that we perform the CSIMS. We can see that when we using the cyclohexene, the O bond, there is no double bond here. Now it's bind with the peroxo fashion. Peroxo moiety bind with the cyclohexene, and the ESIMS at 398.2. When we using the cycloheptene here, that bind with the peak at around 412.2 because of this moiety, and we are using when we using the cyclooctene, and that peak shifted to 426.2 because of this fashion. And after that we are using the ESIMS of isolated 2-cyclooctane using the 16 and 18 O label. So for the 16 case, we can see here is a 426.2 at for peak for the M by Z this ratio. When we using that 18O, that 4 unit shift will be there. If it is 4 unit shift will be there, that is definitely there is a peroxo moiety is there. If it is peroxo moiety, that's why 2 oxygen is there. Because of 2 oxygen, this shift to 4 unit. If it is no 2 oxygen, it cannot be shift to 4 unit. Now, in the enzyme, we can see that in the enzyme there is a naphthalene dioxygenase in the biomimetic chemistry. So here it's responsible for the cis dihydroxylation. This is a very challenging reaction. So in B case, if the people proposing that yes, iron 3 hydroperoxide is formed, but iron 4 oxo 5 oxo is also responsible for this intermediate. But in our case, directly peroxo is responsible for the system. Then in Professor Ramaswamy first published this naphthalene dioxygenase. So we also tried reaction with using naphthalene. So here we can see when we using the chloronaphylene, it also shows the reaction with chloronaphylene. That means our model is very correlate with the naphthalene dioxygenase type of enzyme. We also perform with the bromonaphthalene, same it shows the reaction, and also with the nitronaphthalene, it also shows the reaction. Then how we know this reaction is happened? Then we perform the CSIMS, and after CSIMS we can get, yes, we can see here the CSIMS of the naphthalene bind, chloronaphylene bind of moiety. So when we using the 16 O2, then we can see here the peak at 478 and 482. But when we change that species, that it also change, and this is the stimulated and experimental species there, M by Z ESIM. That also the rho value is plus 0.69. This is also positive value suggested that the reaction going through a nucleophilic pathway. And here is the mass CSIMS for using the bromonaphthalene and nitronaphthalene. So we can see also when using the bromonaphthalene, the peak at 522.1. When we using the nitronaphthalene, the peak at 589.2. So this is the overall reaction for this. First we prepare the iron 12 TMC, and with presence of H2O2 and TAT, first peroxo is formed. That peroxo is reacted with the styrene and naphthalene. Even the different kind of alkene also formed the adduct first, then we added acid there. That acid with presence of acid take proton, this adduct converted to the diol species. So this is the best example for the dioxygenase species here. So after that we perform the product analysis. Then how we do the product analysis? This is the peak for the adduct. So when we added acid there, this adduct directly convert to the green line. That means it releases the diol species. When we check the NMR, for the NMR we prove that yes, there is a diol present in our solution. And after that we also check the product for the cyclooctane. Then cyclooctane with the NMR we quantify, yes, there is a cis diol present in our solution. And what happened to the iron species when we added to the acid to the diol species? That released the cis diol and it converted to the iron 3 species. So 464 and 157 species for the diol, that iron 3 species for this. And this is the EPR, and the EPR also suggested that yes, this is the iron 3 species, that is not binding with the diol. And now the question is, yes, So we have the different kind of system that 14, 13 and 12. Why this kind different system gives a different kind of reactivity? So here 14, as I uh, previously told you that this is the nucleophilic reaction, and 13 case it shows the electrophilic reaction. When we go the 12 case, it shows the dioxygenase type of reaction. So every structure having the unique property and it shows a different kind of reactivity. So now we are focused why it is happened. So after that we using the 14, 13 and 12. So in 2011 we published that the aldehyde deformulation in Nature 2011, and after that 2021 we published JAX for this system, and 2023 we also published JAX for this system. Now the question is why? What is the influence for the 12, 13 and 14 when bind with the iron? Why different kind of reactivities happen? So after that we perform different kind of reactivity using different kind of reactivity using this 12, 13 and 14 system. For the first we generate the intermediate using peroxide species. We can say for the 670 nanometer for the 12 case, when it increase the temperature, you can see little bit shift when blue shape to that shape. And after that we also perform different UVVs for that. For the 670, that is 12, the absorbance is 670 nanometer. When we using the 13 TMC peroxo, that absorbance is 695. When we using the 14 TMC peroxo, that absorbance is. When we plot the, also record the resonance Raman, we can say here is also clearly shift is there. So 514, 503 and this. So for the 1, you can see this is the 12, 514. When we using this 13, that is the 503, and when we using the 14, this is the 493. And when we plot the energy versus the RN oxidation, we got the linear plot. That means something is there in this reaction that influenced our reaction. So after that we perform the DFT of the starting. So starting in the peroxo, we can see when we using the 12, the plane, when we perform the plane here, the distance for the plane and iron is 1 angstrom. When we using the 13, then the oxygen and that plane distance is 0.584 angstrom. When we using the 14, that plane is 0.415. That means there is a decay, there is a simple phenomena that if it is 12, the ring size is less, that the plane iron is too much away from that ring. If we are going increase the ring size, then iron goes to the cavity of that iron center. Same case we perform the DFT for the 12 TMC. Then you can say average plane for this 0.9. When we using the 13, 0.7, and then we using 14, 0.6. That means in the peroxo case also there is a trend. So something that trend influence our reactions. So after that we perform the MCD, and the MCD suggested that this iron binding with the oxygen with a sigma bond fashion. Now how sigma bond fashion influence the reactivity? So we perform the iron oxygen bonding interaction complex 1, 2, 3. 1 is the 12 TMC, 2 is the 13 and 3 is the 14. So in this case we can say there is some change in the binding with the iron and the oxygen. And after that we perform the reactivity for the 14, 13 and 12. You can see there is a reactivity, the Ki is 3.1, 3.5 for the 14 case. When we do reaction with the 13, the Ki is increasing, that is 6.0. When we using the 12, the Ki is also increasing, that is 7.6. So after that we check the temperature dependent kinetic study of 14 TMC and find that due to the iron plot we find the K2 for 3.7 10 raised to power minus 4. So after that also 13 TMC we perform the kinetic, and the iron plot we find the K2 for this and 13. When we compare all these things, you can see here iron 14 TMC, the rate is 3.7. When we using the 13, the rate is 5.6, 10 raised to power minus 3. When we using the 12, that's 6.5, 10 raised to power minus 1. You can see there is a reactivity, huge difference in the reactivity. That means there is a something influence, that is the size of the ring influence their reactivity study. And after that we perform the DFT, and after DFT we perform, yes, this is the reaction coordinate, this is the Rn 12 TMC. First we perform two type of reaction, this is Rn First, this is transition state. It convert to O, this iron oxygen bond cleavage, and convert to iron to superoxide species. Another one we using this O bond cleavage and convert to iron 3 dioxyl radical. And dioxyl energy you can see there is little bit higher. So that means during the reaction, that peroxide species first converted to the iron 2 superoxide species, and that superoxide react with our substrate and gives the product. So when we plot all this energy barrier, you can see there is a sigma orbital of the CH that we can using the cyclohexadiene, and there is a pi star orbital of oxygen. When we compare this reaction for the sigma H orbital and the pi star orbital for case of blue, that is your 12 TMC, very close. But when we use that 12, 13 and 14, you can see the distance of this too high. That means this one is 12, 13 will come here and 14 will come here. That means it is not easy to give electron here easily. That's why there is a change in the reactivity. So here is the all why different peroxide species give different type of reactivity. We are focusing on there. So that is the oxygen plays very important role for the different kind of reactivity, even the nature as well as in our catalysis and the simple stoichiometric reaction. So now here is the thing. So how we generate the metal oxygen intermediate, and which kind of intermediate it generate with the oxygen. It is superoxo, it is peroxo, it is hydroperoxo, it is oxo. Different kind of reaction is happen there, and different kind of intermediate give different kind of reactivity. We have to focus on that. So our research was related to this intermediate, this kind of intermediate. First we generated and check the reactivity as well as the catalysis and find out why the nature choose this kind of intermediate and correlate this kind of intermediate with our system. So now, so this is the simple, we can generate oxygen intermediate with a different, even using the synthetic oxidant as well as the oxygen. If it is generated, then how we can play with the different kind of roles like enzymatic biomimetic system as well as the catalytic system as well as our stoichiometric reaction. So here I am acknowledged to my PhD supervisor, Professor Alan Mukherjee. He was the professor in IIT Kanpur. Now he is retired. And here is the Professor Van Boonam. I did postdoc Professor Van Boonam under Professor Van Boonam, and now he promoted me as a professor in his lab. Thank you everyone for your kind attention. And if you have any question, please ask me the question. And finally, I am thankful to organization committee giving me chance to present my work here. Thank you so much.
Anyone, please ask your questions. Any doubts? Anyone? Sir?
Yes.
Thank you, sir.
Welcome. Thank you, ma'am.
Thank you, sir, for your wonderful session.
Yes.
Wonderful session. So now let me give you the information on metal oxide intermediate, dioxide activation, combination chemistry. So your session is ready. Dr.
Thank you, ma'am. Thank you so much.
So we have wonderful information regarding dioxide intermediate, sir. So your session is excellent, sir.
Thank you so much, ma'am. Thank you.
Thank you, sir. Thank you once again.
Thank you. Thank you, ma'am.
So, accepting our invitation, sir.
Thank you so much for giving me the opportunity. Nice to contact within the future also. Thank you so much.
Okay, sure, sir.
Thank you.
Now I request Dr. Sister Ramal Bedi, HOD of Computer Science, to propose vote of thanks.
Good evening, everyone. As we draw close of today's enlightening session of 5-day International Webinar-cum Faculty Development Program on Innovative Approaches in Green Chemistry for Addressing Emerging Challenges in Chemical and Allied Sciences. It is my privilege to extend a heartfelt gratitude to all of you. First and foremost, I extend my sincere gratitude to God for His benevolent blessings all through the session. Now, I owe my gratitude to keynote speaker, Dr. Srinivasa Rao, Professor in Department of Chemistry, East Point College of Engineering and Technology, Bangalore, for his thought-provoking insights on green analytical chemistry approaches on environmental analysis and sustainable development. Sir, your inspiring words have given us a broader understanding of green chemistry, and we are indeed grateful for your valuable time and knowledge. I would also like to express my deepest appreciation to Dr. Akhilesh Kumar, Professor at Eva Women's University, South Korea. Thank you, sir, for your engaging session, for sharing your vast expertise. Your contribution has enriched today's event, leaving us with much reflect and to implement. A special thanks to our beloved principal, Dr. Sister Shaini KP, for her warm and continuous support for this initiative. Your leadership has always been a guiding light for us. My sincere thanks to Dr. G. Jyoti Olivia and Dr. V. Sumalata for introducing the chief guest and to the organizing committee for your unwavering dedication and efforts in making this event successful. To all the participants, thank you for your active engagement and enthusiasm throughout this session. Your presence made the discussions more meaningful and productive. Lastly, I would like to thank our technical support teams for ensuring smooth functioning of this virtual event. Without your efforts behind the scenes, none of this would have been possible. With that, I extend my gratitude to everyone once again, and I look forward to second day International Webinar-cum-FDP on Innovative Approaches in Green Chemistry for Addressing Emerging Challenges in Chemical and Allied Sciences. Thank you all. Have a wonderful evening.
Thank you, sister, for your information regarding the first day of webinar. Thank you, sister, once again. Thanks to all the participants.
Feedback form is posted in the WhatsApp group. You are requested to fill the feedback forms. Thank you.